Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, I'm Sanjeev Arora, and I'll talk about provable bounds in machine learning. Now, I should say at the outset that I'm not an expert in machine learning. I do theory, algorithms, and complexity, and this is a fairly new interest for me. So I actually taught a course at Princeton in the spring, which is called "Is Machine Learning Easy?" And so this is a very condensed version of that. And the operative word here is provable. So machine learning is a very flourishing field, and there are a lot of techniques, but and there are people who do theory of machine learning, but there's also applied machine learning, and there's not a whole lot of connection between the two, because as we'll see in today's lecture, the concepts used in applied machine learning research inherently lead to intractable problems, NP-hard problems or worse. And so it's been very hard to develop provable approaches for machine learning, and we're trying to do that. And in today's lecture, I'll introduce this broad area and maybe point to ways in which you can have provable bounds. Okay, so let me start by saying what's machine learning. What do you think was machine learning?
Machine that, given the interacting with the user.
Yeah.
And some information stored in it, it could learn how to predict the next activity.
Okay. Predict the next activity. Okay. It's interesting.
It's a way to predict the next activity to learn. How to learn.
Is that how you would describe human learning? How would you describe human learning? How would you describe human learning?
Just with some practice, training.
And
Supervision.
ability to connect known to unknown. Known to unknown. Okay. Any other thoughts? Learning through experience. Experience is an important part. Yeah. Yeah. Identifying a pattern. No, but think about human learning, right? Well, yeah. Okay, so I think maybe it modifies a way for a computer to modify or improve its behavior / improve its behavior using data / experience. Okay, it sort of captures what many of you were trying to say. Many definitions. Okay, there's just one definition. So actually, it's funny. I was talking to an old friend who's a professor in English, and she asked me, well, what was I working on these days? And I said, I'm working on machine learning. And she said, machine learning? And she was thinking something like, improving the behavior of toasters or something like that. I guess that qualifies. Because machines for her were like things with gears and levers and so on. Okay, so but we are computer scientists here, so yeah, machines are computers. So example, Example given user data, users data, predict what movies they like, right? Movies they might like. Okay, so this is a kind of thing human experts who like movies can do, right? They look at they understand movies and what kinds of movies they are, and then they look at users' data, like past movies that they've seen and what movies they might like. So things like this, right? So yeah, I think everybody has seen this. AI, what we call AI or machine learning. Now, it wasn't clear to people, certainly in history, how to even quantify this. And the dominant paradigm in modern machine learning is that of probability. Is the dominant paradigm. And what do you think of as probability? What does probability mean to you? But in general, not just in this context, what do you think of as probability?
What is probability?
Yes.
The chance of a given event being happening. So it's basically a given, the number of times a given event happens divided by the total number of times, summation of all the events.
Okay. Okay. So this is the frequentist definition of probability. So the frequentist definition of probability is if you want to know, I don't have a coin on me, if I toss the coin and it comes up heads 53%, 53 times out of 100, what's the probability it comes up heads, right? It's 0.53, right? That's your estimate. So that's a frequentist definition of probability. Anybody can think of any other ways in which we use probability? Quantifying uncertainty. Like, what's the probability that it rains tomorrow? Well, there's only one tomorrow. So the frequentist definition is one. So probability is inherently a philosophically tricky concept. Once you start reading, I can point you to literature on that. And here, there is an element of frequentist interpretation of probability, but there's also the subjective interpretation, okay, just quantifying uncertainty. And that comes from the Bayesian view, okay, that there's some set of possible worlds and you have some preconception of what kind of world you're in and what's the range of possibilities, okay, whatever. The kinds of worlds that are out there from which some sample is drawn that you're given. Okay, so it's all it's a subjective theory, okay, that's sort of all in your head. So let's not try to think too much about it, although it's impossible to escape it. I'm just warning you because what you'll see next. Okay, so all right. So yeah, this is the subjective Bayesian version. Okay, and some of the best minds of mathematics over history have struggled with the notion of probability, and it took a long time to work out, all these confusions because different people have different meanings of probability. And I wouldn't say it's even now all worked out. If you start thinking really hard, you can come up with some very paradoxical notions. But it won't matter so much, the paradoxes of probability here. So right off the bat, let me introduce this, with a very provocative example of what this Bayesian view is. Okay, so example. So there's a die which was tossed, okay, many times, and the outcomes is a number from 1 to 6, right? You took the average of those numbers over all the trials, okay? So die was tossed a few times, or tossed a few times, or many times. Average outcome, meaning the number from 1 to 6, the average was, say, 4.7. What is the probability that it comes up? Okay, so a die was tossed many times, and you took the average of the outcomes, right? Each outcome was a number from 1 to 6. You took the average, and the average was 4.7. Now I'm asking you, what is the probability that it'll come up 6? Sorry, there was an answer here. What? These are independent tosses. No, this is not a fair dice. Yeah, it's not fair. That's why the average is 4.7. Yeah, it's not fair. Yeah, you're in Las Vegas. There's not enough information for you to answer. Was there another suggestion? Sorry? No, it's not unbiased, no.
But there is 6 on the die.
Yeah, the numbers are from 1 to 6, yes.
Well, the probability of 6 can be 0.
Can be 0, indeed, right? I mean,
It may not be possible to
that's right. It's so badly loaded that it never comes up 6, right? It could be, right? It could be, right? So it could even be 0, because 4.7 is less than 5, so it could be that it always comes up from 1 to 5, and 5 happens a lot. So the average is 4.7, so 6 could be 0.
So do we know the number of times that's been tossed?
100, let's say. Yeah. That's not going to be the key point here. Right? There's not enough information, right? So it could be 0, it could be whatever, right? You can give lower bounds and upper bounds, yes? Cannot be 1, yes. Okay, we know that. Yeah, so that's we can say some things, right? It must lie in some ranges and so on. Sorry? Yeah, sure. So that's the upper bounds and lower bounds. Yes, you can compute some upper bounds and lower bounds. Okay. All right.
Prior probabilities, calculate prior probabilities and then calculate the posterior.
So what is your prior? So the suggestion is have some prior probabilities and then calculate the posterior. What's your prior?
Uniform prior.
Okay. So there's the Bayesian approach to this. Okay, so that's the one being alluded to, that you have some kind of prior on all possible worlds, and you have some kind of prior based on the fact that it's in Las Vegas, and people in Las Vegas, when they load the dies, construct them in a certain way, and so they have, there's some kind of prior like that. And so based on that prior, now you've observed something that tells you something about the construction of the die, and now you use Bayes' rule. Bayes' rule is this rule. Probability of A given B is the probability of AB. Probability of B. So using this rule, you can update things and you can do a calculation. So I won't do that because I want to do something even more radical than that. Okay, so that already you can see is a very subjective interpretation, right, of probability, right? That you had in your mind some kind of distribution on the set of possible worlds out there. Okay? How did you get that? From experience or whatever. Okay? So I'll do an even more radical thing here. Okay? So it's called the max entropy principle. Okay. Which is that the posterior distribution that you got some kind of a measurement of the probability space. So you got this measure, the average was 4.7. And now your estimate of the posterior is going to be the probability distribution that maximizes the entropy, subject to whatever you know about this distribution. Okay? By the way, this was called many times independently. I said it, but I didn't put it here. Okay, so max entropy principle is that your guess of the distribution is the distribution with maximum entropy among all the distributions consistent with the facts you know. Distributions consistent with known facts. How many people have not seen the concept of entropy, the information theory concept? Okay, so I'll just describe this function for you. So in this case, entropy just means the following. So the distribution in this case is some set of numbers, P1, P2, P3, P4, P5, P6. Right? The probability that it comes up 1, 2, 3, 4, 5, 6, right? So that's the distribution. And of course, the sum of these is 1. Right? That's what it means that it's a distribution. And the entropy is equal to minus summation of pi log pi. I equals 1 to 6. Okay? That's the entropy, the definition of entropy. Am I writing big enough for the people at the back? Is it fine? Maybe this one was a little small. This is log base 2. Pi log base 2 of pi. Okay, this is a very fundamental notion in information theory. It represents the number of bits you need to represent an average sample from a distribution. So we won't go into the information theory interpretation. It's just a function, okay, like this. It's a measure of the, as the name suggests, the amount entropy at. Okay, have people seen entropy in physics or thermodynamics or something? So people who had not heard this in the context of probabilities, that they've seen it in the context of physics? Is anybody who's not seen entropy in either physics or in information theory? Everybody's seen it? Okay, so it's this. It's a measure of the amount of randomness in the distribution. number of bits needed to represent the average sample. And so the feeling behind this maximum entropy principle is that this is the only thing you know, and so you don't know anything else about this distribution, and so you posit that the distribution, the true distribution, is the one with the maximum entropy. Okay, because that's a distribution which maximizes your ignorance, subject to all the things that you do know.
Yes, subject to the mean being.
Subject to the mean being, yeah. So here, in this case, it'll be namely the P1 through P6, such that summation Pi is 1, summation I times Pi is 4.7, and you're trying to maximize minus summation Pi log of Pi. Should probably move this for the people over here. Okay, so you find the values of P1 through P6, which maximizes nonlinear function, the entropy, subject to the two known constraints. Okay, now all of you, I know the Indian system, if one thing they teach you, it's very good calculus, so I think everybody knows how to do this using the method of Lagrangian multipliers. Okay, so yeah, maybe that's the homework. Compute that P1. Yeah.
Is there a way to compute this distribution in time function?
Excellent question. So, right, in general, we don't. Yes, that's a big problem. Okay? That's a very big problem. Okay, so like everything in probability theory, the maximum entropy principle is, has its controversies, people who believe in it, people who don't. Any responses to this? Yeah, oh, you have a question? No. It is, yeah. So the form is something like, yeah, because there are logs here, yes, you will get exponents in the description. In general, you get exponents of some functions. Yeah. Any responses to this maximum entropy principle? It's sort of conjuring up stuff where there was nothing, right? I mean, all you were told was that was this, right? And as you notice that doesn't tell you what's the probability that it come up 6. But here, this method will give you a precise answer. Okay, so it's sort of making up stuff where there wasn't enough information to know that stuff. Yes?
So, this is the principle. What is the guarantee that this gives you the best answer?
It's subjective, yeah. So I put up this ridiculous notion just to prime you already that there is a very fundamental issue here about, throughout machine learning, and throughout many other statistical estimation things like, testing the effectiveness of drugs or something. There's these kinds of issues that arise in all of those. That you're making up stuff, to put it completely plainly.
So are there any examples where, it works really good, like in experiments in which it has actually found to be, follow the really closely or something?
No, I mean, it cannot, right? Because you could be in a world where, as people pointed out, whenever somebody makes a die with this property, 6 never comes up. Okay, but the point here is the principle is saying then you know something about the world, right? If you observe that your world is at variance with your prediction, incorporate that information and come up with a new prediction.
So that's a known fact, right? So we are choosing from among the distributions consistent with known facts.
That's right. So now if it doesn't match reality, now you examine reality and see, why didn't my prediction match reality? And then you learn something about reality, and then you put that constraint in and maximize entropy and continue doing that. And after a certain number of times you do that, there's nothing else you don't know about reality. And then you would presumably be predicting correctly. Okay, there's nothing else that can be known about reality. So so this principle is used in linguistics a lot. We won't use this much in these lectures, but we'll use something sort of reminiscent of this, which is the next thing I'll talk about. Okay, so actually let's look at this example. So we're done with this. Okay, let's look at this. So the Netflix, Cynthia, did you already mention the Netflix problem today? You did, okay. So a different aspect of Netflix problem, namely, the original scientific problem that was given. You were given users' ratings of movies, and you had to predict what movies they might like. So one way that people modeled that was as follows, that there's an unknown matrix. Okay, so this was the Netflix problem. One view. So there's a matrix with users and movies. So whatever they are, 10,000, 100,000. No, that's more, right? Whatever. All the movies in the world and all the users in the world. And then each user, you posit that for every user, if you show them the movie, they'll have some rating from 1 to 5 or whatever. Of course, not every user will see every movie. So, and then also all the number of users you have data about will be some small portion of this matrix. So you get to see some portion of this matrix. Okay, so given some entries of this matrix, predict some other entries. That is, in a nutshell, the scientific problem being posed. Right? There was some matrix, a huge matrix. You don't have access to most of it. Somebody gave you some entries out of it. For some users, some of the movies that they've seen and liked, right, or whatever, the ratings. And from that, you have to predict others. Okay? So for some other user, you might know that he or she liked these 10 movies, and based on that, you have to predict what other movies they'll like, right, or not like. So, any thoughts? Sorry? No, but you see, what I'm trying to make you think of is, that in all of this, you have to make up stuff, right? So you can take off-the-shelf buzzword, right, collaborative filtering or whatever gee-whiz software, right? Microsoft probably has some products for this, probably internal, right? And put it in, right? You can do that. But I want you to focus on the scientific underpinnings here, okay? Here, I'm telling you there's a matrix. I gave you some of the entries. Predict the rest of the entries. How would you predict it? Can you predict it?
Link it from similar movies and similar users. Come up with the notion of similarity. Can you impose some
Okay, let's take away the movie setting for now. There's a matrix, and I give you some of the entries. I ask you to predict the remaining entries. Can you do it?
Can you constrain the matrix to have identical row sums or column sums or something like that?
Let's say, okay,
Some constraint.
fine.
And then once that constraint is imposed, you are reduced to a finitely many possible choices.
Yes.
Is that the way to go? Or?
Well, the finite is very high anyway, and I mean it's whatever. This is, I don't know, millions of entries, so number of matrices is 2 to the power million, you know, whatever. It's a very high number, but so among those choices, how do you choose? Okay, so now you're imposing some structure, but first let's just think about it as a matrix problem. There's a matrix, unknown, then you're given some entries in this matrix, you have to predict the others. Any suggestions here?
Starting from the base, if we are not using any constraints, and if I use the matrix and I average the values corresponding to the particular column or something, if we are missing values, then I can average over the rest of users to predict that rating. This is the lame method irrespective of using any constraints. And then we can introduce the concept of likes and finding similar groups, or like which are the similar movies that are being liked by same.
Okay, so let's go to the movie in a minute. I'm first asking you just to say about matrix. There's an unknown matrix. I give you some of the entries. I ask you to predict the remaining entries. Can you do that? No, right? You have to make up stuff, right? It's like this problem. There's not ever information in the statement of the problem, right? To let you compute any of the missing entries. The ones you haven't seen, who the heck knows what they are, right?
Yes, but I can still use the entropy argument.
You can use a maximum entropy principle, or you can do other things, yes. Or, okay, so at least at the matrix level, there's not enough information in the problem, right, to solve it. There's paucity of data. Okay, so just even in principle, you cannot do it. So now, okay, let's go to so if you think of it as movies, you can impose some prior information, right? That this movie and this movie are similar, right? Or and so you're saying that you'll compute some kind of a similarity score that if you like the same kinds of movies, you can predict what other things you like. But now I want you to think of the following. So suppose the number of movies is, I don't know, 100,000, right? And let's say each user rates 50 movies. Okay? And suppose, just randomly 50 movies, right? What's the chance that you'll see any two users where there's substantial overlap between the number of movies they've seen? Very small, right? This is a very tiny sample out of 100,000. So you'll never see users who like a lot of the same movies. So next idea. What do you do next? Okay, so even with that information, there's not enough. Even with that, idea, there's not enough information in this problem.
This is not valid for sparse matrices because the amount of data is unknown.
No, let's say the matrix is not sparse, right? Because in principle, every user would have an opinion about every movie if they saw it, right? It's just that they haven't seen too many movies and they haven't rated them for us. Right, so there's not enough information. That's the bottom line, right? And now you can make up stuff. Okay, just as we made up stuff here. You make up stuff. You have assumptions about the world, domain knowledge. You have some model, probabilistic model for how these entries were selected. Okay, and we'll see some examples of that. And then you can come up with some number, okay? And it's a number, right? This user will like this movie. and this is the predicted amount of liking they'll, what they'll rate that movie. You can come up with a number, right? But you're conjuring this number out of thin air. Okay, I just want to emphasize that. Okay, in machine learning, there's not a unique answer, and the answer depends on your assumptions and your methodology. Yes.
As against the previous example, in here you have exponential many events, right, that you have to mention upon.
That's right.
Isn't a single statement that you can state that?
That's right. You're saying if, let's say we try to use maximum entropy principle or something. Yeah, the calculation is hopeless, yes. Yeah. So, yeah, so this is not a very, this is, in some information theoretic sense it makes sense, but computationally there's a huge cost. The moment the number of possibilities is exponential, I mean, forget it. You can't do this. At least not this way. Okay? All right. Is there a clock? How fast? Oh, this one. Half hour. Good. Okay. By the way, a couple of homework things for you, which might actually explain something. It certainly explained something to me when so this is homework. What is max entropy distribution whose mean is mu? Any guesses? Discrete or continuous? Could be continuous. Continuous, let's say. Exponential? Yeah, that's correct. Huh? So it's a distribution which has a distribution like this, e to the minus x over mu. Okay, that's the density function. Second, with mean mu and variance sigma square. Positive, that's right. That's right. I think there's an analog for when you allow negative too. It's not this one, but okay. And this one, mean mu and variance sigma square? Normal, okay. And mu sigma square. But you have to prove it. I'll give you a link to an article, so it's more of a self-study than really proving stuff. Maybe a third one is graph with this is a discrete distribution. Graph with m edges. So if I just tell you there's a graph and has m edges, okay, n vertices, n edges. Sorry, I wrote too low. I'll try not to write that low. But all I'm saying is graph with m edges. If that's the only thing you know, what's the maximum entropy distribution on graphs on n vertices consistent with that information? Any guess? Not regular.
Ring are fully connected.
Sorry?
Fully connected.
No, we don't know any of that. Just the number of edges. Yeah. So yeah, it's just the uniform distribution over such graphs. Which is, with high probability, the uniform distribution on such graphs will be fairly regular, whoever said regular. But that's not, we don't know that. So not every graph will be that, and just the maximum entropy distribution is just a uniform distribution on graphs with m edges. Okay. All right, so so we won't do much with maximum entropy, but it'll lead to the next thing we'll do, okay? And it was just, I put this up here because it is used in linguistics, which we won't do. That's an important aspect of a part of machine learning. So we won't do much more of this. We'll do maximum likelihood. Okay, in the settings that we'll be interested in, we'll be using maximum likelihood. So what we'll have is something called the maximum likelihood method. So you're given data, like this data. And what you have to, as I said, you have to make up stuff. And what's the stuff that you have to make up? You need to have some kind of an assumption about how the data was generated. Okay, something about this domain, right? Some knowledge, domain knowledge. So that's called a model. Okay, so there's a probabilistic model. Model for how data was generated. Okay, and then find the model parameters. Probabilistic model with some parameters. Okay, by model I mean there's some parameters. Okay, this is parametric or parametrized. You find the model parameters that best explain the data. And what does it mean, best explain? You'll be using max likelihood. And it's another one of these principles which, if you look at it, it's not clear at all. You know, just like with the max entropy principle, which is sort of related to max likelihood. It's not clear that that's, you know, that it's the only way you could have proceeded. Okay, that's the only methodology, but it's a popular one, and I'll describe it to you. So let's do it in a very simple example. Example: Gauss's least square fit. How many people have never seen least squares fit? Okay, a few. And a few over there. Okay, so I'll describe to you. So, you know, in high school or wherever, you learned about drawing a graph, right? There's an x-axis and a y-axis, and you take in your lab you took some observations, and you were supposed to infer the relationship, right? This is force, and that's acceleration or something, right? And you're supposed to infer the relationship. And so you look at these points and you say, it looks kind of like a straight line, so you fitted the best straight line, and you just eyeballed it, right? What the best straight line is. You leave a few points on one side, few on the other, and roughly in even proportions, and then that's your fit, right? So, well, Gauss, like many other things, you know, Gauss thought about such things as well, and he gave you sort of the best way of doing it, which I'll describe now. And, you know, again, you have to make up stuff, okay? So you make up some reasonable assumptions, and then it's the best possible fit, okay? So that's what I'm describing. So the data is, I'm doing it in a very, very simple setting that most of you have seen, just so that you can focus on the important new thing you might be seeing today, which is max likelihood. So data is x1, y1, x2, y2, xm, ym. And the model is that there exists a b, some numbers a b, namely the numbers describing the straight line, such that y and x lie on that straight, xy lies on that straight line. But not exactly, right? There's noise. And so what's the noise you'll assume? Gaussian, right? Gauss is doing it, so it has to be Gaussian, right? So, but that's where the term comes from. That's right. Gauss didn't write in his paper. From now on, this model will be called Gaussian. And some sigma square, variance sigma square. Such that, so that's a model, okay? That there's some A, B, and R such that y equals ax plus b plus eta, where eta is distributed like, this is my symbol for is distributed like, okay? Which I'll use from now on. So eta is a number which is distributed like the normal distribution with mean 0 and variance sigma square. Okay? This means little eta is a random variable distributed according to the Gaussian with mean 0 and variance sigma square. Are there people here who don't know the Gaussian distribution? I should ask that. Is there anybody who doesn't know the Gaussian distribution? I might as well write it because I'll need that for a calculation. So the Gaussian distribution with mean mu is a distribution where the probability of x is, so this is x, this is x, and this is probability of x, and probability of x is equal to 1 over square root 2 pi sigma e to the minus x minus mu square over 2 sigma square. Oh, did you use Gaussian too, Cynthia?
No, that's 2 days ago.
Okay. So that's the Gaussian distribution. I'll need this formula anyway to do the calculations. You might as well do it now. So might as well put it here. Okay, so that's the model, right? That there was some straight line, y equals ax plus b, but and x's were generated who knows how, through some distribution again. We don't even know, okay? Distribution of x is unknown. Distribution of x is unknown. So you don't make any assumptions in this method. And you don't need to hypothesize any distribution, okay? Just so long as there's a distribution. And so you're assuming that x was generated, however, according to some distribution, and y was generated as ax plus b plus this noise. Okay, so that's what generated this plot at these points. And now you have to find the line. Okay, so the thought process in this max likelihood technique is the following. Suppose the model, the true parameters were these, right? A, B, and sigma square. What is the chance that you would see the data that you actually saw? Okay, so probability of generating the data given A, B, and sigma is proportional to the product over I. Remember, the data is this. So product from I equals 1 to m of the probability of generating each individual data point. I'm assuming that the x's were chosen distribution and they were independent. Or no, actually, I don't even need that. I don't need independence among x's. So I just need that these Gaussian noise were this. So for each x, a new right. So I should have said this, that the noise is independent for different xi's. That's very important. Okay, so it's not the same noise. It was implicit in my picture here that for every x, for every data point, you generate a new noise, right? The deviation from the true line. So it's exactly this, right? It's proportional to the exponential of minus y minus ax minus b. Okay, so eta is just y minus ax minus b, right? So minus 1 ax minus b squared over 2 sigma squared. Okay? So that's the probability that you generated the data if the parameters were A, B, and sigma. So the data that you saw could have been generated by many different models. Okay? And for each of those, there's a certain probability that the data was generated, and it's proportional to this, right? So this part is the same for everybody, sigma. This is the only part that varies. And, oh, I apologize, x, what was x here is this. Okay? Is this clear? Ask a question.
Say that training data given AB sigma as well as x size, right? So when the x is known, then there's the probability of getting this.
Oh, right. Sorry, I have x size. I'm sorry. Thank you. Is that what you mean? Yeah. That's what.
I'm saying that we get this data given the x size.
Given the x size, that's right. Yeah. Right. Okay, you're right. Thank you. Given x1 through xn. Thank you. Correct. Any other questions? Okay. So now, the max likelihood principle says that pick A, B, sigma that maximize this probability. Okay, this is the likelihood of this data from the unknown parameters, and so you choose the parameters that maximize this expression. Okay? That's the max likelihood principle. That among all possible parameter values, you pick the one that maximizes the chance of producing your data. I must admit, every time I see this, it makes me a little uneasy, more than a little uneasy. Okay? So you have a set of parameters that produce this data with probability, 1%. And then there's another set of parameters that produce this data with probability 0.5%. That's not a big enough difference for me to just prefer one unambiguously over the other. Okay? It could be even more, right? 1% versus 0.099%, 0.0099%, right? So two things which are very close. And why should I pick one? This could be a very different set of parameters than this, and their likelihood is sort of the same, and somehow you're getting one number out of it, okay? One set of parameters. It seems very arbitrary. Okay? But this is the calculation that's done in like 50% of machine learning algorithms. Likelihood, max likelihood. Makes me very uneasy. Even the principle, I'll tell you why it makes me uneasy. The principle, right? That's not clear, right? Even in this simple setting. And then, actually applying this principle in most settings will lead to very difficult problems, computational problems. So people don't know how to solve those either. But okay, so finish the story. So now, okay, the rest is homework, okay? Because you've all seen the minimum, the least square fit. That's exactly what it'll give you. Okay, which is clear, right? Because right, you're looking at, it'll pop out when you do the calculus. All right. So that's a simple example of max likelihood. And and as I said, for me, it's all of machine learning. That's what people do. There's a model for how the data was generated. So for the Netflix or whatever, all of these problems, there's a model. You come up with a model. That's where you're making up stuff, number one. Okay? So that's the first place, in your model. How the data was generated. There's a model, parametric model. So you made up stuff there, okay? So maybe I should enumerate. Okay, so making up stuff. Okay, by making up stuff, I'm saying it a little pejoratively, but it's what a domain expert does. Okay, to solve the problem, they throw in things about
Sigma is the square root of variance. How can we pick it? We have the exercise defined. So can we pick
sigma? The sigma will be just. So there's only proportional. There's also a sigma here. This one. When you do the calculus, it works out. Yeah. So making up stuff. Okay. So number one, there's the model. Model for how data was generated. Okay, and this uses domain knowledge. Okay, so I don't mean to, this step, it is unavoidable, right? You have to use domain knowledge, and you have to encode that domain knowledge in some mathematical way, and that's the modeling step. Yes?
So each term is the probability that beta is equal to y minus x minus b?
That's right.
So it's a continuous distribution, right? So probability that beta takes a particular value is 0 for any value.
Yeah, but you're trying to no. So density. I guess you're maximizing the density at that point, right? That's the probability density at that point, at this data point, right? You have a m-dimensional data point, right? So there's a probability density at that point, and you're maximizing the probability density. Yeah. For continuous distributions, you have to use the density. Was there another question? Okay, so that's the first step of making up stuff. The second step is the maximum likelihood assumption. Okay? Just the assumption itself, if you think about it enough, makes you a little bit uneasy. Okay? At least something to think about. You're just making up one, you're saying you prefer one set of values for the parameters over all the rest. And then the third thing where you have to make up stuff is actually solving this MLE problem, okay, which in this case is not so difficult. You can do it by simple calculus very efficiently, but in general settings leads to intractable problems. MLE instance. Okay? And here people also make up stuff because many of these problems are NP-hard, and so they make up stuff. They don't actually solve it in any kind of rigorous way. Not in the kind of way that Ravi would, Ravi Karan, but also our Ravi, the previous lecturer, would approve of. Okay? There's not a principal sort of approximation guarantee or anything. Okay? It's just you code up stuff and hope it works. All right. No. This calculation isn't needed. Yeah. For any set of x's, the choice of, yeah. Okay, so let's see where intractability arises. Okay, so. Yeah. Excuse me? No, data was given. Data is one thing we don't make up. Yeah. Okay. Okay. Yeah. Yes.
So is there so far we have not even spoken about how good it is to the actual data there is no measure of how good the distribution what we have.
That's right. So there was a suggestion, there was a question before, how well does it do in practice? Well, there's no good answer to that, right? Because practice could mean whether you're in Las Vegas or in Bihar, whatever, right? So therefore, you would use the maximum probability method, right? Do a prediction. It doesn't match it. Well, then you say, okay, it doesn't match reality. So where was I diverging from reality? And then you'll use some more knowledge about reality, put that in, and again apply max likelihood consistent with that new information, and so on. So this is just in principle you can do this, okay? The max likelihood, and this is sort of, in some sense, optimal. What you could do. All right. What was that? Right. So why do intractable problems arise? So let me give you some examples. So let's see. I can erase this too. So if I was writing a play, the stage direction would be enter intractability. So, yeah, you can imagine the moment you have multivariate distributions and now you're describing data using some multivariate distributions, these parameters are not so simple, lots of parameters, and the likelihood function is some highly nonlinear function, and now optimizing that will be in general NP-hard. How many people, I guess everybody's seen NP completeness here, right? This is the theory audience, right? So you've probably seen that nonlinear optimization very quickly gets NP-hard, in the very simplest cases. So you'll get NP-hard problems. So let's just see some examples. So mixtures of Gaussians. Of even identical Gaussians. Oh, these are multivariate Gaussians. So simplest multivariate Gaussian is just where all the you have a vector where all the coordinates are univariate Gaussians, independent univariate Gaussians. So where mu is in the end. So the ith coordinate is distributed as the Gaussian with mean mu I and variance sigma square. Okay, that's the ith coordinate of the vector. So you have a vector. So it's a distribution, multivariate Gaussian. It's a distribution on n variables, so n coordinates. It's a vector. The distribution is on vectors, and the ith coordinate is distributed according to mean mu I, the ith coordinate, and variance sigma square. Okay, so to draw a three-dimensional picture, you could have these. This is some kind of a, not very good at three-dimensional, this kind of a bell curve in two-dimensional, sort of three-dimensional bell curve. I don't know how the shading is. And there's another, and mixture means that the data is generated according to, so if it's a mixture of three Gaussians, uniform mixture of three Gaussians, it means that 1/3 of the data was generated according to one Gaussian, 1/3 according to another, 1/3 according to the third. The yeah, this is an example. Yeah, this I can't draw more dimensions. Yeah. Uh-huh.
So wouldn't mu and say the ith coordinate, the mu and be a.
Oh, right. Sorry. What's the correct? No. What do I want to say? You're right. What's the correct notation? Yeah. It's not that. Sorry. It's yeah. I don't know how to. Okay, so all I mean is, I think everybody sort of, I hope understood, which is that you have some point mu, and in the ith coordinate you have this distribution. Okay, I'm blanking on the correct notation for this. Ravi, you know? Spherical. These are spherical, right? Yeah. How do I want to suggest that it's? No, not the 2 pi and so on, but like. No, it's the same variance everywhere. It's same variance. Okay, I can do it in the matrix notation, but I want to do it without matrix. Okay. Anyway, I think people got the idea, right? So it's just, you have mu1, sorry, okay, so here you have a mixture of, let's say 3 Gaussians. So there's mu1, mu2, the second mean, and mu3, the third mean, and you have a Gaussian around each of them. And 1/3 of the points are generated by this Gaussian, 1/3 by this, 1/3 by this. So this happens, for instance, if you look at the distribution of heights in the population. So you could say that the population is half male, half female, and males and females, their heights are distributed according to Gaussians. Well, that's not quite true, but it's an approximation. At 2 different means, right? The male mean and the female mean is different. Okay? But here we are assuming that the means are different, but the standard deviation is the same. In all directions. It's a multivariate Gaussian. Okay? So I still don't know a good notation for this, but I hope I talked about it enough that you understand what I mean. Okay, so now if you're given points, x1, x2, So these are vectors, xm in Rn, determine max likelihood Gaussian Gaussian mixture that generated it. So to go back to my example of heights, you're given data points involving heights of people, and you want to identify the two underlying Gaussians, namely the male and the female Gaussian. Okay, so if you look at some distribution of heights for the population, so this is height, and this is the fraction of people who have that height. And what you'll see is some kind of a superposition of these two Gaussians. Right? It's something like a bimodal distribution maybe, or something like that. And then you'll say, aha, I can see that it's a mixture of two Gaussians, one centered over here and one centered over here. Okay? So statisticians do this kind of thing. Okay? They look at the population and try to determine the component Gaussians, for instance. Okay? So there's just a one-dimensional example, but you can do it multi-dimensional. This is a very basic model in machine learning, mixture of Gaussians. Okay, so now the likelihood for means Gaussian mixture of k Gaussians. K Gaussians. So I'm given some number k. Okay, here k was 3. So I'm given some number k, and I'm trying to find the best mixture of k Gaussians that describes this data. The max likelihood mixture of k Gaussians that generated. So likelihood for some parameter values. Values mu1, mu2, mu k, and sigma square. I'll continue over there. Yes?
Yeah, I'm a little confused. So k, do we take any k? I mean,
No, k is given to us.
as a k.
Yeah. So you're told as part of the problem what k is. Okay, so this is going to start reminding you of, I can tell you right away. I think Ravi talked about facility location. Did he say k median at all? Okay, so it's going to be like k median or k means. Okay, so here it is. So you have these k points in space, right? Okay, I can only draw two-dimensional, but there are these k parameter values, mu1, mu2, mu k. And now you have I don't have different colors, do I? No. So you have the data points, right? Okay. Now, so for each data point, let's say you identify the mean. So you're trying to write the likelihood expression for given these means and the sigma square. So for each data point, you would have to say, okay, assuming it came from this mean, what's the chance that that Gaussian would have generated it? Okay, so for each x1 through xm, you assign C1 through Cm in 1 through k, which is just which Gaussian generated it. Okay, so if this data was generated by the Gaussian, there's for each data point, there's a number from 1 to k which says which Gaussian generated it. And so now the likelihood expression is just likelihood is proportional to something like exponential of product from I equals 1 to n of exponential of minus xi minus mu sub ci square over sigma square, something like that. Oh, I'm doing one thing which I should have introduced earlier. Sorry, I'll do that now. I went from univariate to multivariate and I forgot to do one thing. Let me just do that here. So what's the, so if you have a multivariate Gaussian like this, and I have a point x, what's the chance that this Gaussian generated x? Since I have, so now I'll do a product over all coordinates, I equals 1 to n, of exponential of, in the ith coordinate I have a Gaussian with mean mu I square over 2 sigma square. Right? That's the probability density, right, at x from this Gaussian. Okay, and now it's a product and a product of exponentials, so the product becomes a sum. Right? So this is equal to exponential of minus sum over I, xi minus mu I square over 2 sigma square. Right? Sum over coordinates. What was product over coordinates becomes in the exponent sum of coordinates. Okay? Which is just this vector, the Euclidean norm of this vector. Right? That's all I'm doing here. I skipped the steps. I'm just explaining that step. Okay? These are vectors and this is square norm. Yes?
I didn't really quite understand this.
This thing?
Yeah, so in the case of the male and female example.
In the case of?
The male and female distribution.
Yes.
How do you start off with the distribution?
Okay, so in likelihood, in this likelihood calculation, you say, give me any choice of parameters, and I'll compute the likelihood of generating the data according to it. That's what we're doing here. So we have so in this likelihood expression, we are given the mu's, and each xi has been mapped to some mu, and now according to that mapping, we're calculating this. Okay, and so now you have to, so now to max likelihood, would say, find mu1 through mu k, and this C1 through Cm and sigma, that maximizes it. Okay, so that's the answer. So this was a thought experiment. If you were given the mu's, then this would be the likelihood. And now you're trying to find the mu, sigma, and the C1 through Cm, which maximizes the expression. Okay? Now you can see this is very much like this facility location, right? That there are these k facilities you have to open up, mu1 through mu k. And then the objective function has this distance of x to some facility. Yeah.
Isn't this square?
It's square. Square distance, yes. I do have a square up here. Maybe it was too small. Okay, anyway, this is NP hard. This problem is NP hard. For general K. For general K.
And even what dimension is NP
No, fixed dimensions should not be NP hard. Do you know of an algorithm in fixed dimensions? There should be, right? Feels like divide and conquer or something, right? Seems like it. Yeah. Yeah. Fixed K is NP hard, you think?
I would think even K equals 2 because
Possibly.
some small K.
I see. Okay. Anyway, to cover myself, I'll say general K. Okay. Ravi thinks it's even hard for small K, like 2 or 3. So, right. So you just made this problem just a little bit more complicated than Gauss's simple setting, right? Just mixture of K Gaussians, multivariate, and you end up with the maximum likelihood problem ends up being NP hard. So this was remember the third bullet that I've erased, right, of making up stuff. So the first bullet was the model, that's making up stuff, but that's using domain knowledge. The second was the maximum likelihood assumption, that's making up stuff, right, preferring one set of parameters over others. And then the third part of making up stuff was actually solving the maximum likelihood problem, and that's NP hard. And so people make up stuff there. Now you can apply approximation techniques, right, what Ravi has been talking about, right? And maybe he'll even talk about K-median or K-mean. But then it's again not clear, right? If you do an approximation of this objective function, what does that mean, right? Because approximation of the exponent, so it's really a very weak approximation, and maybe max likelihood is this very special set of parameters, and if you only approximate the likelihood, those set of parameters don't make sense. It's a very murky area, what to do. Okay. Any questions? Yeah. Yeah. Yeah, there's a very rich theory of hardness of approximation, yes. I don't know if Ravi will talk about that, yeah. Yes, but that's sort of tangential here, yes?
Each exercise is generated by choosing a random Gaussian and then choosing a random point.
No, so I'm assuming that all these Gaussians produce the same number of points. So like, in the male-female example, it's 50-50. So here, 1 over k of the points. That's why I don't have that expression. Like what's the weighting of each Gaussian? Each Gaussian is equal weighting.
Yeah, so choose a uniformly at random, choose a Gaussian, and choose a point from the Gaussian.
Yes.
So this is the distribution of xi, right?
Yes.
So and the parameters of Gaussians are unknown. Mu is and
That's right. Yeah. No. Yeah.
so the objective is to know which are the Gaussians that were chosen. C1 to Cn.
No, the Gaussians are determined by the means, mu1 through mu k.
Yeah, and the Gaussians that are chosen at the first step was C1 to Cn.
That's right.
So we want to know all of them.
That's right.
That were chosen as well as the parameters of one.
Right, they were chosen for each xi, that's right.
There is a clustering problem.
It's just a clustering problem.
To solve the clustering problem, then you're done. Then you have to fit only one Gaussian to that set. So that's just fitting one Gaussian. So that was the homework.
Yeah, I don't want to do this too much. I mean, I won't do much with mixtures of Gaussians, but Ravi is an expert on these kinds of things. He has some very nice techniques for handling these calculations. Any other questions? Okay, so I want to mention, since I'm giving this broad view, so we have to. So going back to the topic of the lecture, right? Of these lectures, which is provable bounds of machine learning. This is what we have to confront. So where will the provable bounds come in? So we're making up stuff anyway. So we'll have to make up more stuff. Okay, so we'll have to have assumptions. Except we'll just clearly state what the assumptions are, and then under those assumptions you give a provable algorithm, which runs in polynomial time provably. That's the goal. Okay? All right. Let me introduce, since I'm introducing models in machine learning, so a lot of work in machine learning uses what's called the Gibbs distribution. So, thus far we already saw that maximum likelihood, even with fairly simple distributions like these Gaussians, right? Very simple Gaussians, same variance in all directions. That already starts getting very hairy. This is a much more complicated class of distributions. So here, it's given implicitly. So you have some distribution over Rn. And so the variable is x1 to xn variables. And the probability of x is proportional to, let's say, okay, actually, let's even simplify. It's just plus minus 1. So this is a probability distribution over binary vectors, minus 1, 1, n-dimensional. So these are the variables. And probability of x, this vector of variables x, is proportional to exponential of minus sum over, so there's some, something like this, summation ai xi minus summation bij xi xj minus summation cijk xi xj xk, etc. Okay, so it's some polynomial. Okay, some polynomial of some degree. Let's say here it's cubic, and you're given these. There are these coefficients, ai's, bi's, ci's. And the probability of x is proportional to the exponent of this expression. Okay, so Gaussian is a very simple example, right? Gaussian is a subcase. It's a subcase where you just have exponential. Well, okay, here I'm assuming plus minus 1, but if it was real, it would be, right, just this expression, right? Minus summation xi minus mu I square over 2 sigma square, right? So it's a very simple polynomial. But in general, you could have a much more complicated polynomial, okay, with all kinds of different coefficients. And it's proportional to that. Okay? So why do these arise? So these arise, for instance, example, in vision. You're trying to come up with a model for images, okay, a probabilistic model of images. So, what's a random image? Now, a random image is not random values of pixels, right? Because if you take a random image on Flickr or something, right, it's not random values to pixels, right? There's some distribution, right? There's maybe sky in many of them. So a significant fraction of the image is blue, or some variant of blue. So there's some distribution there, okay? So that's the distribution of images. So you're trying to capture it. And so you have these variables, okay? So you have a matrix of variables. And one assumption about this model is that the value of a pixel depends only upon its neighbors. Okay, you can draw some radius, 1 or 3 or 4, but the value of a pixel depends, in a probabilistic sense, only upon that neighborhood. So what that means is that, so this is the so-called Markov random field. I won't do much with Markov random fields in the rest of lectures, but I'm just describing to you some of the things that are out there, the bizarre stuff, right, in a mathematical sense. So Markov random field is that for each I, probability of xi given the rest. Right? So if I fix all the other variables, the probability of xi, right? So the probability distribution of xi. That variable, that conditional variable, is just the probability distribution of xi given the neighbors, values of neighbors of xi. Neighbors of xi. So it's called the Markov random field, that there's a locality to this distribution, that the values of this pixel, if you know the values of all the neighboring pixels, you know the distribution of this. Not the value, the distribution. Okay? It doesn't depend upon values far away. So this is called the Markov random field. Okay, it's the distribution is local in this sense. Okay, but this locality doesn't mean that this pixel is independent of that pixel. Not at all, because it's dependent upon these pixels, and these pixels are dependent upon their neighborhood, and that pixel is dependent upon its neighborhood. So this does depend upon this, but it only depends upon this via this wall around it. Okay, in a probabilistic sense, that's all. That's the dependence. So it's not that this is independent of that. They are correlated. Okay, so even though this is defined locally, the correlations are global. Okay, and so turns out that the distributions describing Markov random fields correspond to Gibbs distributions for some polynomial degree. For some degree. Okay, for each graph there's a degree. So that's a general theorem, Clifford-Hammersley theorem. So there's a theorem in statistical physics. Okay, they study these things in statistical physics. So okay, so you have a distribution like this. Okay, now my point is this. This is made up stuff. Okay, you can't take this too seriously. Okay, maybe if you're studying actually a gas, right, and molecules in a gas, this is all actually the reality. Okay? But now you're using that molecular gas model to study distributions of images. And it's going to be a very approximate description. Okay? This is made up stuff, right? It's a metaphor. It's maybe somewhat close. So all of this is just, this is sort of going from here to there is sort of assuming that general theorem I mentioned in statistical physics, the Clifford-Hammersley theorem, which says that any Markov random field has a description, its distribution is given by Gibbs distribution. That theorem requires a certain precision. If it's exactly like this, then it's like this. Okay, it's a mathematical theorem, and this is the problem. Most of mathematics is about precise descriptions, and here we are all very approximate, and made up, whatever, right? So it's very, very suspect, okay? But anyway, so then you have, this is your distribution. Now just imagine, the most likely, so you fix some of the values of these, and now you're looking for the most likely value of the other variables, okay? So it's problems like this. So like in denoising of images, so you have, or like you have missing pixels in the images, and you're trying to predict them, okay? So by finding the maximum likelihood setting of those variables, you can maybe predict the missing pixels or something like that. So those are the kinds of applications people have in mind, and people do all kinds of empirical optimizations to do those kinds of max likelihood calculation. But what I want to stress is that this is all NP-hard stuff, okay? This kind of optimizations. Okay? And if you're going to try to do provable bounds here, we have to think very hard so that we don't start introducing intractable problems. Okay, I guess I'm out of time. So maybe I'll do just a very quick, I'll just finish that, just in 2 minutes, I'll talk about one way to get around it. Okay, so the point is that max MLE is hard for arbitrary data. You can prove an NP hardness result, and what that means is that for some worst case, very adversarial data points, maximum likelihood estimation would be hard, right? It doesn't say it for the real life data, right? So one way around assume data is itself drawn from a nice distribution. Okay, so then I realize that this may be a very, very subtle shift because you're probably thinking, wait, I thought this is what we were assuming all along. Turns out we were not. In max likelihood, actually, that methodology works for arbitrary data. But if you assume data is itself drawn from a nice distribution, then you can do, it's possible to do in many cases, can do in many cases, polytime algorithms to learn the model parameters. So for the Gaussian case, let me describe quickly and that's homework to verify that this works. So this was an observation of Dasgupta. He had a more general result, but this is a very simple subcase. So if data points are drawn exactly from a mixture of k-identical Gaussians, spherical Gaussians, okay, so 1, and the means are sort of separated. Sort of distinct. Because after all, if you have two means that are very close together, then even in the univariate case, it merges into a single Gaussian. So the means have to be somewhat different for you to say these are two distributions, mixture of two distributions instead of a single Gaussian. So if means are sort of distinct, then can find it, find the means in polytime. So this is a homework problem to sort of put specifics into this sketch. That and the idea is going to be just very simple. I'll just say in one line the idea, which is that for an n-dimensional Gaussian, which is spherical, meaning variance is the same in all directions, if you pick two random samples from the Gaussian, what happens is that these two are basically going to be orthogonal. Okay, and so you can say what this distance is. Okay, very tight. There's a very tight concentration. Okay, this distance is you write out the square. It's the sum of n IID variables. It's very tightly concentrated by law of large numbers. So this distance is very tightly concentrated, and so if there are two distinct Gaussians, the distance from this point to points from the same Gaussian will be less than the distance to points from other Gaussians. So you can show that. Okay, it's not very difficult to show that the distance from this to any point on the other Gaussian with high probability will be more than the distance to the points to the same Gaussian. So you just cluster the points very simply. you just take all the points that are closest to them and put them in one cluster, and that works. Okay, so long as the means of the different Gaussians are somewhat separated, this works. So yeah, that's the homework, to show this property that that if the means are somewhat separated, and you have to compute how much that separation has to be, the distance between points of the same Gaussian is less than the distance between points of different Gaussians. Okay, and then a simple distance-based clustering works. And then once you have the clustering, you can recover the means easily. Okay, so if you actually believe that the points really, really came from a mixture of Gaussians, you can learn them. So that's what Dasgupta was pointing out. Okay, and so this is another extreme of the spectrum. Okay, in mass likelihood estimation, you don't assume that the points behave have any structure, and you can still do the likelihood calculation and come up with some kind of model. Okay, and here in Dasgupta, this end of the spectrum, you're assuming that the points are really coming from the model, and then you're learning the parameters of the model, and that actually turns out is possible. And what you would like is something in between. Okay, something that will generalize to practical settings. So we'll talk about that more in other lectures.